So, hello everybody, and welcome to this talk. In this short presentation, I will give you an overview on reinforcement learning, and I believe that's the next big thing in industrial automation. I will also show how you can apply reinforcement learning on an industrial automation case, and I took as an example an integration into optimization of mobile networks. Well, some words about myself. So my name is Norbert Kraft. I'm with Nokia Bell Labs. I'm located in Munich, Germany. And before we start into details of reinforcement learning and industrial automation, I would like to give you a short overview on Bell Labs as such. So Bell Labs is an organization which exists and has been founded in the late 20s of the last century. That's an unbelievable long time. So Nokia Bell Labs made some very famous innovations and inventions. So for instance, in the late 40s of the last century, they invented the transistor. They also built the first solar battery in the early 50s. So, and they have been very famous for all their work they did. Some years ago, Alcatel-Lucent was acquired by Nokia, and now Bell Labs belong to Nokia as a research institute. And here we are doing telco-oriented, or let's say oriented to our business research in different areas. I'm sure you know that Nokia is in the telecommunication business, so we sell products from smartphones down to mobile base stations for radio access networks. We are building and selling core routers, optical equipment, switches, all kind of equipment you need to set up your core networks in the field. We certainly have different research areas, so we are doing research in access networks, service automation, software platforms and systems. We do a lot of standardization for all these kind of communication equipment. We are active in optical fabrics, and I myself, I'm dedicated to algorithms, analytics, and augmented intelligence, and this is the area I also want to present today. Good, let's talk a little bit about machine learning. So what did we do in the past, and how could maybe reinforcement learning here really a huge benefit and extension? So in the past, we have been doing a lot of analysis on historical data. So we took large amounts of historical data, and we have been doing descriptive analytics. With technologies like supervised learning, we are also able to predict. So if you can take historical data, you can learn from historical data, and then you can make predictions for the near future. I was remembering once a presentation I was giving to one of our customers, where I present a prototype where we did a lot of these analytics from telco data, where we extracted a lot of information. We digged out problems and even predicted problems in the near future. And then the customer asked me, so why don't you avoid problems? So why don't you spend so much time on digging out problems? Finally, I don't want to know what kind of problems I have. Please just make it correct, make it happen, make it working the right way. And last but not least, if you want to do this kind of prescriptive analytics, you need to take control over such systems. So analysis as such is not sufficient. You need to take full control. You should make the systems work the way they should work. So don't detect problems, you should avoid problems. Okay, what are we doing with machine learning in general? So I'm sure you know we have been doing a lot of unsupervised learning in the past. So, and what unsupervised learning does, it finally tries to find groups and similarities and anomalies. You even can you can reduce the complexity of high-dimensional features by reducing the complexity, reduce this to a limited set of new features. The problem with that approach is that you're getting certainly similarities in groups, but you don't get necessarily the understanding for those groups. So it's not necessarily self-explaining. You certainly can, if you have a database of millions of users, persons, you certainly can extract groups, but you finally will not understand on its own what kind of groups you really extracted. So did you extract people which are wealthy? Did you extract poor people, young people, old people, the health with different health status and such? And to identify the groups and get the meaning and the understanding for those groups, this is pretty a problem. With unsupervised learning, we have a nice extension because here we are learning from labeled observations. And those labeled observations, they put some label on our observations we are doing. For instance, maybe you have a data set of pictures, and the label will tell you this picture is showing a cat, or this picture is showing a dog or any other animal. And by combining the pictures and the labels, you put some meaning on it. And by learning this, you can predict later on, if you see a picture, if this is a cat or a dog. So this is a nice approach and much more intelligent as the unsupervised learning. The problem with that is that you need to have human knowledge extracted in such labels. And in my experience, in most cases, we are lacking this kind of knowledge. So whenever you want to learn something, you need a human which takes observations from your machinery and puts labels on it. And this is a time-consuming task, and a lot of practical use cases, this is just not existing. Good, so the next step could be learning from experience. So reinforcement learning really tries to learn from past experiences. So you don't need a labeled set of observation. So the system itself tries to find out how the system it controls is working. It does experiments, it gets feedback from those systems, and it's finally a learning by doing. So reinforcement learning can be a great step and great advantage in doing machine learning in general. So how do humans think? So how does this correspond to machine learning? Also, humans do a lot of unsupervised learning, and they try to extract patterns. That's also what we call instinct. So maybe most people who will see such a picture of a snake will recognize this as something dangerous you should take care of. And this is not learned by experience necessarily, and this is also not learned just from books. So people have a natural understanding of danger and patterns they should avoid. What are we doing if we are doing as a human supervised learning? Finally, we are reading books. So we are learning from others. We extract knowledge from text, and this is used to train our brain to act accordingly. And also reinforcement learning has a one-to-one relation to our human thinking, because if you ever watched a kid learning to walk, you will see this has to do a lot with learning from experience. So walking is not given for a young child. It has to learn this by trial and error. It learns it from past experiences, and step by step it's improving, and finally it can learn, it is able to walk. It's also interesting to have a short look how we think, so how we are computing inputs in our brain. So we certainly have sensors. We have eyes, we have ears, we can listen, we can see, we have tactile sensors, and we take this information and together with some thinking what we think is positive for us. So we have a reward thinking. We know maybe food is beneficial for us. We also have an idea what's not beneficial for us, and we take those different inputs, so observations and reward information together, and we are deriving actions from this. And finally, our brain is also optimized for optimizing rewards for us. So to take the best food, to take the right food, and these are all our actions. And this is based on observations and rewards. So we have a lot of similarities of machine learning and real thinking in a human brain, but there are also differences. I'm sure you know that maybe a neural network is a try to imitate human thinking. And if you compare those different approaches to detail, you will see a lot of similarities. Also, human brains and neural networks, they have this kind of feed-forward processing. But the human brain also does a feed-backward processing. So it's also processing the other way around, so in the opposite direction. This is only partially true for neural networks. You have these kind of RNN or LSTM networks, which have some feedback loop as well. But in plain neural networks, you just have a feed forwarding. Also, the complexity is much different. So we have by far more neurons in our brain than we are able to implement neurons in a neural network today. Interesting is also to compare the switching speeds. And here the big surprise is that our brain is even slower in the switching speed than the switching speed of neural networks on modern computers today. But nevertheless, the human brain structure is very hierarchical, whereas the neural network is pretty flat and simplistic. And last but not least, finally, the human brain is massively parallel. So we can do thinking in parallel and forwarding in parallel, whereas the neural network is still serial. You also have parallel processing on GPUs and fast engines, but we are still very limited compared to our brain. Good. This is not all. So if you think about these kind of thinking we have in neural networks and the human brain, you can certainly compare switching speed and complexity, but we are far away from imitating a human brain. So, you know, there is a lot about intuition, instinct, gut feelings, mind, emotions, intellect, and things like this. We do not fully understand, and we are not able to imitate in a neural network. Good. Now let's stop with those let's say, basic kind of thinking. Now let's go into deep into reinforcement learning about the basic ideas and the algorithms. Well, reinforcement learning has the idea of having a controller, which is an independent agent, and a system, which represents an environment. And those two entities, they communicate to each other, whereas the system generates observations, state information, and also a reward information, and sends this to a controller. The controller itself is taking this information and derives an action out of this. And the controller then triggers an action in the system, and this causes the next round in the same way as before. There are some basic principles how this interaction works, and the way it is going to be. So first of all, the controller and the system, they don't have any kind of knowledge about each other. So the controller does not know what kind of system it's controlling, and the system has no idea what controller is acting on it. So the controller always starts with a random action because it doesn't have any knowledge when at the very beginning. So finally, it's a trial and error learning, and the controller tries to optimize the reward he gets. The states in the agent and in the environment are totally hidden, so no one knows from the other one what kind of internal states there are. The controller receives observations and reward and triggers the next action, whereas the system receives this action, goes into the next state, generates new observations and reward. So this is the whole way this system works. That's a pretty simple model, but you can certainly apply this on a technical machinery. And this is an example how you can apply this maybe on a mobile network, on the telecommunication network. Well, our telecommunication networks is a pretty complex system because here we have mobile base stations for broadcasting the mobile signals. We have internal switches, routers, we have optical transmission systems. But what we are doing since long time, so we are extracting state information out of this. That's what we call low-level KPIs. So we are extracting alarms and error rates. We are measuring throughput per user. We are measuring events showing errors and problems and things like this. And what we also derive is that we extract high-level KPIs. So we try to measure what's the overall performance. So what is the overall throughput per user in total? What is the total power consumption and things like this? Our controller is made out of systems with graphical desktops where we extract thousands of values and measured entities. And we have humans sitting in front and operating this network, trying to fix problems, trying to detect problems. And last but not least, this is really done by humans. They are experts. They must be very well informed about what they are doing here. They must have a good understanding of standards, of technical issues. And finally, what they do, they change parameters. They change the transmission power of such a radio cell. You can switch, you can set up different scheduling algorithms, set priorities, bandwidth parameters. You can even change the coverage area of such a mobile radio cell that you have more or less users in it. So, and this is all done to optimize the total behavior of the network and to make, last but not least, our customers happy. So this is the model applied of reinforcement learning and applied to technical machinery like a telecom network. Well, some formalisms. So as I said, so we have this controller and we have the system, and they act with observations, rewards, and actions between each other. And the controller by itself has three major functions in it. First of all, it has a policy function. And the policy function takes an observation and derives the next best action to take on this observation. And there's also a value function which makes a prediction. What kind of reward do I get if I see a state and a corresponding action to this? And what is the expected reward I will see in the next step? And last but not least, we can implement a model, which is more or less a transition model of all those states and actions and rewards together, and gives you an idea how the complete machinery works. Not necessarily every controller must have all these functions. You have controllers which only have a policy function and a value function, or only a value function and a model, or just in other combinations. So these are just ways you can implement a controller, and there are different approaches to do this. An important fact in reinforcement learning is also the exploration, because you have to explore the system, which means if you see a state, you must try several actions to find out what is the best action to take. So if you have a state and you have 5 possible actions, you need to try every one of those actions to get the best one. And the only thing you can do at the very beginning, you can try to use a random action. Maybe you can also use an action you have never checked before. You can also run through those actions sequentially. Last but not least, you have a huge amount of observation and action combinations you need to try out. The other important factor in such a reinforcement learning agent is exploitation, which means you're taking already known information to maximize the reward. So you take things you already learned. So if you know that based on a certain state, action 1 gives me a very big reward, it's useful to take this action again if you are coming back to the same state. And now you have this dilemma. So you must do exploration to explore the full space of possible values, states, and actions, but you must also try to reuse information you already have seen, so to get an optimum. So in some cases, you also must use this information you already learned to get better actions to achieve that your system is converging and is coming to a final state which is more optimal than before. And that's the dilemma here. You must do a lot of exploration to explore all possible state action spaces, but you must also use exploitation. And so if you're doing too much exploration, you will have no convergence. And if you're doing too much exploitation, you will never see a global optima. Another important factor in reinforcement learning is you have to consider the action and observation space and how big those spaces are. The good thing is if you have a limited action observation space, maybe you have a system which only has 4 different states, and you might have maybe 4 actions you can apply to this system. This is a very limited one. You simply can implement such a solution maybe with some straightforward algorithms, with tables, with simple decision trees and regression techniques. The problem comes up if you have an unlimited or nearly unlimited action and observation space. And this comes, for instance, if you have a system which gives you an observation vector which consists out of 100 or even thousands of different values. And if those values are real numbers, so they are in a range from 0 to 1,000, and so you have a huge space you need to explore. And on top of that, if you have maybe 100 or several hundred different actions you can apply on this state space, you only can solve this by using neural networks, deep learning techniques. So this is a very important factor. Also, discounted future rewards is an important topic. So you certainly need to consider the reward you get for a certain state action pair. But you also need to consider what are future rewards I might get if I go into the next state. And so there are 2 ways. You can only consider the next reward you will get. So this is some kind of short-sighted evaluation, or you are taking all future rewards as well, maybe with a discount factor. And because you might do a move into a next state which doesn't give you so much or big reward, but maybe based on this state, you might get much more rewards because you are in a very optimal and a very good state in general. So in most cases, you have to consider the reward for the next step and also those rewards for future steps. I only want to introduce you one way which is very famous. That's a so-called temporal difference learning, or also Q-learning approach, which is a nice formula which implements this kind of reinforcement learning. Finally, a Q function represents the expected reward for the state action pair. And based on these experiments you are doing, you always will override and take the old Q value you have seen so far. You also put a learning rate into that and add in this new state action space the maximum reward you have seen for the future one, for the future action state space. So, and by applying this formula on a value function, you step by step, you are learning how the system behaves. Good. Let's stop with theory or basic thinking, how reinforcement learns in general. And now let's think a little bit more about how you can apply this on a mobile network again. So, as I said, what we're doing with mobile networks, so we have these thousands of base stations in the field. We have a lot of other systems like routers and optical systems, and we are deriving KPIs out of that. So today, this is a human process. So we have humans, operators doing this. They are supported by systems with lots of graphical desktops collecting all these values, which is also pretty demanding applications. And they have some hard-coded SON algorithms, and SON stands here for self-organizing networks. These are optimization algorithms which are hard-coded, which have been invented by developers. The problem with that setup is, first of all, network experts are rare, so it's not that easy to find people who have the right knowledge of radio technologies. So yeah, they get a huge amount of information. So maybe a German Telecom in Germany has about 70,000 radio cells, and they are extracting every 15 minutes about 150 values for every radio cell, showing how well this works and what kind of problems arises. So you're getting overwhelmed by this information. And at the same time, you also have maybe thousands of parameters you can modify. So you can change the power, the broadcasting power of those stations. You can set up tilts and other informations in those cells to make it working better, much better than before. But last but not least, we have to say today, most of these networks are in a suboptimal state because the task is nearly impossible to solve to really optimize this in every flavors. So how could this look in the future? In the future, we could replace those hard-coded algorithms, or also a lot of people doing this optimization. We could replace this with autonomous self-learning network optimizers, and they should be certainly based on advanced artificial intelligence machine learning methods, especially on reinforcement learning methods. So they should be totally autonomous without any manual interaction. They should smoothly improve the network during operation. They should be self-learning from experience they made in the past. And they should be also programmable, which means you must be able to program them to optimize for different directions. So you might optimize for high throughput, for low power consumption, and things like this. Okay, so this is the basic idea, what we would like to achieve. And now let's take our knowledge of reinforcement learning and let's see how this could be made together with a mobile radio network. For such a prototype, what we have been building in the last months, so we took a simulator because we didn't want to connect this directly to a real network. So because this is a prototype, this is research work, and we didn't want to disturb a real running network. So we took a RAN simulator, which we have been developing in-house for a long time and also for other purposes. Finally, this simulator simulates a complex radio network consisting out of a different number of radio cells, and they have a certain location, they have a transmission power, they have a certain well-defined behavior. Between those radio stations, you have buildings which implement and influence the coverage of the radio cell. You certainly have user groups moving around between those cells, and these users using user entities which are simulated smartphones with some random traffic. So they might do FTP downloads, they might raise a voice call, and doing other activities in this network. And last but not least, the whole simulator generates a huge amount of KPIs, what we can use to generate our low-level KPIs, and also to generate reward functions based on these KPIs. And finally, what the controller does, it's able to change the parameters of those radio cells, transmission powers, algorithms, and priorities. So this is our whole setup. So how can you now implement such a controller, such a reinforcement learning controller? An interesting thing here is to look at, are there standardized software, is there software available who already can be used for that? An interesting candidate here is OpenAI. So OpenAI is, first of all, a private-based company in Silicon Valley. It's a company funded by Microsoft and some venture capital. Their idea is to build software, free software, for training, benchmarking, and experimenting with AI, especially for AI, for autonomous systems. And they also deliver this for others to benefit from this. And they're also doing a lot of research and cooperate with universities. There are some alternatives to OpenAI, so companies like DeepMind, which is very famous in this area. They also have done a lot of inventions and IPRs on these technologies. There are projects founded by Google and Microsoft, and there's also a lot of open source software. But OpenAI is really an interesting candidate to implement such a reinforcement learning control agent. So what's given by OpenAI? So first of all, it's an interface definition, and this is an important part because you have two systems to interact. You have an agent with an optimizing algorithm, and you have an environment which should behave in some way. And OpenAI defines an interface, how an RL agent and an environment should interact. So how should observations be exchanged, and how do you trigger an action and things like this. OpenAI also provides a so-called GYM. These are ready-to-use environments which you can take to evaluate reinforcement learning algorithms. On top of that, it provides reinforcement learning algorithms. They call these baselines, and here they are very famous algorithms like deep Q networks, actor-critic methods, and things like this. So a reinforcement learning has the same set of standard algorithms like standard supervised learning. So in supervised learning, you have decision trees and SVN networks and those names, and in RL, you have DQNs and actor-critic methods. So this is well known. So we don't have time to go very deep in those algorithms, but you have a ready-to-use set of well-known and well-understood algorithms. So on top of these systems, the environments and the algorithms, you also have a so-called baseline zoo, which is a set of successful trials. So setting up those systems, environments, and algorithms, you have a lot of parameters, and it's very useful to see successful trials and understand what are the parameters which really achieve those good or bad results. And on top of that, OpenAI provides a huge amount of resource extensions, open source extensions like algorithms, environments, tools, and beside that you will find a huge amount of papers, benchmarks, and tutorials how to use this. Well, let's have a look on the different kind of environments OpenAI provides, and they are certainly pretty simple ones. Let me start one of those here. Actually, this doesn't work in the presentation here. Sorry for that. The card poll is a, let me try this again. Unfortunately, I couldn't start the video here. Sorry. Sorry, I can't show this. So the card poll is an environment where you have to keep this card poll in the upright position, and you can you can introduce actions where you can move the card poll more to the left or more to the right. There are also games in these environments, maybe the Lunar Lander. This is just a game. You have to land the spacecraft between those two flags. Or you just can play tennis games, robot applications, and also even simple computational algorithms for sorting and changing string patterns and things like this. So this gives you a nice introduction on that. I'm also not able to get this started here, unfortunately. I'm sorry about this, but I can't start this video because this video shows how a reinforcement learning agent has been approaching this problem. And finally, you will see that the spacecraft is really able to land between those two flags. And now it's working. So with that video, you can see after a certain time of training, the system is really able to land this Lunar Lander between those two flags. It looks a little bit shaky, but finally you can see that the reinforcement learning agent was really capable of doing this. Good. Now let's have a look on the whole system, what we have been using. Remember that we wanted to integrate this mobile RAN adapter, which is called Season, mobile RAN simulator, which is called Season, into this environment. So what we finally did, we took this RAN simulator and we integrated this in the OpenAI environment. Beside the others you have already seen, these compute, robotics, games, and control applications. So we integrated this, and now within that environment, the season adapter, the mobile RAN adapter, is visible in the same way than the other applications we have had a look at on this as well. Beside this integration, we also developed two environments. One is called an OpenAI tool, and one is the so-called an OpenAI desktop, which I will show a short overview about these two functions later on. And on top of these OpenAI environments, which now include a mobile RAN simulator, we have the algorithms which are provided by OpenAI. And here we have actor-critic methods, DQN, SAC. These are well-known algorithms in the RL world. We also developed some own algorithms, which I don't spend time today on. So we also invented our own algorithms based on this OpenAI environment. Let's have a short look on what these two tools are used for. First of all, the OpenAI Baseline is a basic tool which instantiates such a gym environment with hyperparameters. It gets a so-called baseline. It starts a random walk through the system just by selecting random actions. Then it selects a specific RL algorithm and a policy. It trains the model, and finally it evaluates the model. And last but not least, it generates a database about the whole run, because those runs are running for hours or days. And finally, you must collect a lot of information to find out if this was something useful or not. And for getting this out, we also invented this OpenAI desktop, which is finally a dashboard application where we can load all this data which has been recorded through training and evaluation of the algorithms, and where we provide graphical views. And this is very important because you need to find out, especially with such a complex system like a mobile radio network, if you really have been successful optimizing this. And this is not that simple, because you don't see this just by looking at one parameter. You have to have a look on different parameters. So this can become a very complex task. So finally, the whole system looks like this. So we have this RAN simulator, which is called Season, which is a very complex application which simulates all these kind of user movements and smartphone usages in mobile RANs. This has a very complex configuration. So we put on top a reinforcement learning agent, which is looking for the action spaces and observation spaces and translate this into the world of OpenAI algorithms. And finally, the algorithms can instantiate such a mobile network. It can step through, and step is a function which takes an action and receives in the next step a new observation and also a new reward. Well, and last but not least, the whole thing is generating an offline database, and this offline database can be read by the RL agent desktop, which is just a dashboard and which is showing you what happened in that environment. Now let's have a look. What is the outcome of such a run? And what did we really achieve by experimenting with this? So what we implemented in this mobile RAN simulator is a scenario what we called Hamburg Port Network. So we have a cooperation with the port in Hamburg in Germany, which is, I think, the largest port in Germany at all. So here we have been simulating a radio network in that port. It's consisting out of about 60 base stations spread over this area of the port. And here we have different user entities which we simulated. They are moving between those different entities. And last but not least, what we wanted to achieve is an optimization. So, and this is shown in the upper part of this slide here. If you look to the left one, so we have 3 cells, and maybe the 2 blue ones. They are unbalanced, which means you have one cell which has a huge amount of users. So this is potentially overloaded, and you have another cell which is maybe nearly unloaded. So there's just maybe a single or very few users in that. And now by changing the size of that cell, and you can achieve this by changing the transmission power or the tilt of the antenna, So you can lower down the cell which has many users, and also make the other cell a little greater, which has much less users. And finally, you are shifting users from one cell to the other. So this is what we call the load balancing. And by adopting these parameters based on the actual traffic condition, you can achieve that the network is getting much better balanced. And it's also getting balanced automatically by an algorithm. Now let's have a look to this desktop. And here you can nicely see, so these charts here on the lower side tell you something about the throughput per user, which has been measured in the whole network. Remember, we have about several hundred users and about 60 radio cells. And here in the blue phase, which is the so-called random phase, so here the agent just selected random actions on these tilt configurations, we achieved about 1 megabyte of throughput. And in the yellow phase, we started to learn. And here you can see that the throughput is going to be improved step by step. And finally, in the evaluation phase, after the training, when the training was finished, we just evaluated the existing model. You can see that we achieved a higher throughput per user than in the states before. So this shows you first, we have been learning. So we learned to improve this network, and finally we achieved a higher throughput. Now you might think this is a pretty small change from 104 megabit to 107 or 108 megabit. So this is maybe just a 5% improvement. I can tell you, if you are able to improve a radio network of such a size to 5%, this is a big deal, because you're just achieving this by optimizing parameters. You don't achieve this by putting more resources, which are very costly, into this network. So this is a big thing. In the next step, you should also look what really happened to the sites. And here you can, by the way, this is showing you some KPIs which we extracted from these radio networks. And on the right side, you see the downlink average user throughput in bits per second. And you also need to know that every user entity requested about 1 to 2 megabit per second. This is how the simulation works. And then you can see in the green boundary, you will see in those sites, every row now represents a radio site, that all these users are getting the throughput they requested. But in the red rectangle, you will see even in the lowest sites, site 04, site 05, you will see that those users got only a small fraction of the throughput they requested. So you can see they are even going down to 700 kbit. So in total, it's not that bad, but you see you have certainly some radio cells which behave pretty bad. And if you switch now, and this was the initial state before we optimized it, and later on we did the same evaluation after this training. And then you can see that in the worst cell, in the site 04, the improvement was made from 740, I guess, was the number, to 850. And so in that cell, we really have a much bigger improvement. So we have an improvement of about 15% just by changing those parameters. So although this looked as a very small improvement, finally the whole network has been improved a lot, because in those cells where we really had problems, we improved the throughput by 15%, and we have been doing this just by optimizing parameters. And this has been done autonomously, so without any human specialist intervention. A very important factor is also, if you're doing such kind of optimizations, you must look also to other values. If you just look to the throughput, you might run into trouble, because let's make the assumption, if you have an overloaded cell, the simple thing would be to make this cell really small, down to maybe just half the size of the coverage of that cell. So this improved this cell pretty much. But finally, you will lose users, because you will have users which don't have any coverage anymore. And for that reason, you must also have a look to other factors, maybe to the number of connected users in the whole network. So here on the left side, you see, and the green line is my state after the training, that you can see I improved my throughput to 107 megabit per second. So that's okay. That's what we have seen before. But at the same time, you must also have a look to the number of connected users. You must also have a look, did I have the same amount of connected users after my training as I had before? And here you can see the numbers are very small. The difference is very small. So we have 14.67, and before we had maybe 14.75 or so. So we nearly have the same amount of users in the system again. So we really optimized something. And this is a very important point. Good. So this is our prototype. Let's come to some conclusions. So in that talk, I wanted to show to you how you can apply reinforcement learning for industrial applications. So it's very important to have these steps because it's self-learning, it's autonomous, and I believe this would be a big next step in any kind of industrial automation. And I hope you can confirm that this kind of model of self-learning autonomous controller interacting with the system in a well-defined way is really a way of bringing in much more intelligent solutions into the field. Finally, the whole thing imitates human thinking, this kind of trial and error learning. And I guess in the future, we will see a huge field of applications of this technology to any other different areas. So finally, our reinforcement learning doesn't care if you are optimizing a radio network or if you're optimizing an engine in your car, a gas turbine, or any other kind of technical machinery. So now I'm coming to an end. This was my last slide. I would like to say thank you, and I'm sure we will have in this call now a Q&A session where I can answer your questions. If there's any interest for further information, please contact me. For that reason, I put my email address here on the last slide. Thank you very much.
Fantastic. Well, thank you so much for that, that very informational talk. Always interesting to see how such advanced networks use all the awesome tools out there to utilize their resources in the best way. I have quite a few questions. Are you with us? Are you on the call?
Yes. Good evening. Hi.
Good evening,
Norbert.
Hey, how are you? Welcome, Norbert.
I'm fine.
Well, good to meet you, at least virtually. Right, let's go look at some of the questions, shall we? We have a few questions, and I think we have about 8 or 9 minutes for the questions, and then we'll go to a short break, and then we'll go to the draw. Right, first question. Hi, thanks for the interesting speech. In case something changes in the setup of the problem, like an additional effect which was not in the beginning, how fast is a reinforcement learning technique able to adapt, and how do you react to such cases in relation to the customer?
Okay, so I didn't talk about how long our training phases are going to be. So our idea is, I have to say, we are collecting information from this network in a 15-minute time frame. So every 15 minutes, we get new information from the network. And this cannot be sized to shorter time because this is too much effort within the system. So we have every 15 minutes new type of information. And we have a requirement from our customers. So if they would apply such an optimization, it should be ready in 10 or 14 days. So in roughly 2 weeks, which means you have 15 minutes period, which means you have 96 evaluations per day. And in 10 days, this is roughly 1,000 evaluations. So after 1,000 evaluations or state action pairs, you must be better than before. Otherwise, you haven't done a good job. So this is the periods we are thinking. So within 10 days, you should be done.
All right, thank you very much. Okay, more or less, optimization of mobile networks was always the big challenge for operators and vendors like Nokia, Nokia's engineering teams. Has reinforcement learning started being implemented in live mobile networks for optimization? And if yes, how encouraging are the results so far? And in your opinion, what is the big challenge right now?
Yeah, so we have optimization modules. So we have a product line which is called self-organizing networks, but these are hard-coded algorithms. So there are people doing R&D, they are developing those algorithms, and this is delivered to our customers. I think our increment is really to have an autonomous general algorithm which can self-learn, which can apply self-learning on those networks. So this is the new step. So we haven't tried this prototype on a real network so far. And I have to say, this is really a research prototype. And we are now in the process of handing this over to our business lines, introducing this. And I have to be, and honestly, I have to say, there are still some concerns. So if you tell an operator that we are doing some kind of trial and error learning, they would hesitate to use that. So you have really convinced people that you're not disturbing something. So so you have to be very careful, and you have to ensure a smooth transition from one state of the network to a new state. So I think we need to convince people a little bit that such an autonomous algorithm can do the thing.
I wonder if sometimes, you know, if it's an issue of how we communicate to the customer, because in effect, there probably is trial and error, because that is what the AI is doing, I suppose, or the and so it's more a case of instilling that confidence in the customer that the trial and error is actually the science.
Yeah, I have to say, I think it's not plain trial and error. So you can also do be more intelligent in performing these trials. So you can try to find trust regions where you are really sure that you are better than before. So you can do a lot, which is much more complex than just randomly choosing an action. So
okay, right, now there's a final question which has more to do with human biology, which I guess, you know, to an extent our networks mimic human biology, so I guess it's a valid question. How do we define, or how do we understand that the operation of the human brain is really massively parallel? Could we say that it is somewhat serial, but at working at such high speed of processing and handling of different operations that makes us believe that we operate as parallel? And where is this massively parallel operation ability of humans based on?
That's not that's not so easy to answer for me. I'm not a neuroscientist, you know. So I think the understanding on how humans think is not really coming to a final end. So there are a lot of things we do not have a clear understanding. So our thinking is also influenced by emotions. But to have a model how emotions influence our thinking, that's not a very easy thing. So, and I'm afraid we have not a clear idea how this works. So I just wanted to show with my slides, there are still a lot of limitations in our understanding of our human thinking. And maybe just this reinforcement learning is one imitation of a child learning something with trial and error. But there are things, much more things still to be done. So,
Norbert, thank you so much for that that great keynote. Superb information over there. It makes us really think about what's coming and how things are operating currently. And that's so superb. So thank you so much. Enjoy the rest of your Friday.